Welcome, everyone. Thank you for coming. I'll have some people streaming in. I am entertained by the fact that this is still a little bit like high school and that everyone avoided the very nearest chairs. But you know, that's the way these things play. Kevin, I won't go much into bio, even though I enjoy making him blush.
Don't.
Yes, exactly.
Don't.
But he's, I'll say just this simply. Kevin is one of the very few people I've seen when he came and joined LinkedIn who improved both the immense quality of the engineering at LinkedIn, the strategy of the engineering, and the scale of it on all three vectors, joining, years into it. And that, it's a very rare achievement. And then, of course, when Satya and Bill met him for the first time, they called me immediately after and said, "Don't you think he should be the CTO of Microsoft?" And he was like, "Yes, that's a good idea." So now let's actually start with the learnings around Copilot, because there may be awareness here about what's going on with Copilot, but the fact is it's a lens into the changing paradigm of how coding and engineering development is going to work overall. So why don't we start there? Describe a little bit of what's going on with Copilot, and then describe how this is going to change how development is done.
Yeah, I think there are a couple of things to be learned from the Copilot experience that are relevant to folks who are building machine learning systems or companies around AI. So for those who don't know, GitHub Copilot is a programming assistant tool that can take natural language prompts, like you can express a program you would like to exist, and it generates code for you. And shockingly, the performance of the system is improving at a pretty steady clip, but when we made it generally available a couple of months ago, it was producing more than 40% of the code that its users were producing overall. So it's, and qualitatively, like one of those tools where someone gets access to it. Not everyone, right? There are people who don't like GitHub Copilot, which is fine. But like many of its users are like, this is so valuable to me, you will get it from my cold, dead hands. So, two interesting things about Copilot. One is when we started development on it, we had evidence that large language models were actually going to be able to do this translation from natural language to code. And even when we showed people inside of Microsoft that like this might be possible, we got a range of reactions from, no, this isn't real, like this is impossible, like it's never going to work, to like maybe it'll work, but I'm highly skeptical. And so a big part of what we had to do was to overcome that sort of negative bias to actually get going, because we had evidence not only that it was going to work, but like we had a really concrete plan for how we were going to make it better and better and better over time. And so I think that is a thing that we're seeing across the board with these foundation models. Like people sort of look at them and, there's certainly a degree of hype around them, but there's skepticism that they actually are going to be useful for the things that people want to build. And I think the second thing, maybe the more profound thing about GitHub Copilot is like it is just one Copilot of a potential very many. What we were able to do with Copilot of automating this particular type of, not even automating, just sort of assisting people with a particular type of cognitive work is going to be just directly applicable, replicable to a whole bunch of other domains. So like any sort of repetitive cognitive work is likely going to have a Copilot in the future. And like the model that powers GitHub Copilot, OpenAI's Codex model, really does let you think about software development in a different way. So like there is now a mode of software development that you can do, which is having a conversation iteratively describing an application into existence. So it's not like one utterance or one prompt generates an entire program, but like you sort of say, like, here's what I would like, it generates something, and you're like, okay, like that's good, but like augment it in this way, change this way. And so like it's a multi-turn dialogue that you're having with this system to get like I've got dozens of these demos that we built inside of Microsoft using the API, and increasingly as people get access to the Codex API itself, like lots and lots of people are seeing the power of this.
So first, one part of this, which is, what is this going to mean for the quality of software development? Error rates, security, kind of ability to do kind of new kinds of work, and sort of give a little bit of the lens of what you're seeing in Copilot across these vectors and others.
Yeah, I mean, it's early days, so we will see. I mean, the thing to remember with GitHub Copilot and with Codex in general is generating code with it doesn't absolve you of the responsibility to make sure that your product is high quality and error-free and safe. And so there's still a huge amount of responsibility that lies with the developer or the entrepreneur on just making sure that they're building a thing that is has integrity. Maybe the hardest part of building GitHub Copilot was not the AI bits that translate natural language into code. It was the sort of safety layer that sits on top of the foundation model that looks at the input prompts and the outputs of the model and tries to make sure that it's dealing with like inappropriate biases in the model, that is like dealing with security, that's dealing with safety issues, that's dealing with what happens if the model happens to parrot something that's copyrighted or like under some kind of license that would make it illegal for it to emit what it's potentially emitting. And so like there's just a ton of work that we had to do to like build that layer. And I think there will be more work that we have to do over time. The exciting thing about it is like it does two things. One is it takes developers who are in high demand in a world that has like a boundless appetite for software, and it's like a really interesting tool to help with productivity. But the more interesting thing is I think it opens the aperture up on who gets to be a developer, which can be both good and bad.
Mm-hmm. Yeah.
Like I'm on the good side of the equation, but like mindful of you're going to have a whole bunch of human beings who are going to be able to build complicated things with with this new capability, and like we have to make sure that like you're dealing with all of the security and safety stuff in a pretty rigorous way.
Well, one of the things that's pretty central around all of these foundational large language models is the scale and how they're playing. And, obviously we build these large ones. There's a set of comments I'm going to ask you about that. And then there's also going to be a whole bunch of other ones that are made as well, just because, yes, you're building a, X 100 billion parameter model, right?
Right.
But there's still, like, people can go make and do pretty amazing things with a 6 billion parameter model or a 20 billion parameter model. So say a little bit about, let's start with, what are the implications of the fact that there is this massive scale set of models that a few number of companies can build? And what is the implications in the developer ecosystem and the possibilities in the world from that?
Yep. So, the models are getting, like the foundation models, like the language models, and increasing, like what we'll see this year are like multimodal models, so things that, are building representations of the world across multiple different domains. They're just going to get more and more expensive to build just because it's massive amounts of compute infrastructure required. And there doesn't appear to be a point of diminishing marginal return that we're approaching on scale. So you make them bigger, and I'm making this sound way easier than it actually is, but you make them bigger, and they become more powerful at the tasks to which they've already been put in their smaller incarnations, and they also become broader at the same time. So like they can be used for like a broader set of things than the previous smaller incarnations of the model were able to do. And so like, there's just plenty of incentive to go invest in bigger and bigger iterations of these models, and to like make sure that the foundation that you're building is more and more powerful over time. The way that we think about it, and the way that OpenAI, who's our partner, thinks about this is like we want to make them accessible through APIs, so that you actually have a pretty rich third-party developer ecosystem that's building on top of the models. I don't think it's hard to imagine what individual company, even one that is worth $1 trillion, $1.5 trillion, $2 trillion, like whatever, these big companies are that some of us work for, are going to have enough imagination and resources to build all of the things that can be built that will serve the public good and humanity, and produce a whole lot of value ourselves. And so it's just sort of exciting. Like even I was browsing through the news yesterday, and just the number of excited articles about what people are doing with GPT-3, which is now a relatively ubiquitous thing. It's like 2.5 years old at this point. But like there's just a huge amount of energy around people building things on top of this. And like that's super exciting, and like it just gets better and more interesting over time.
One of the questions some entrepreneurs have asked is, given that there will be a relatively small number of these super scale models provided through APIs, what are the kinds of ways they should think about distinguishing their businesses as building it? What are some of the things that you would think are, kind of ideas and lenses, things to keep in mind?
Yeah, look, so I think, to me, that is the most interesting thing here. So like there is a bunch of interesting computer science and systems challenges, like building really big models. But I don't know that there need to be 15 or 20 platforms out there for things that are going to eventually do substantially the same thing. It'll be good to have a few of them because competition's good, and you want to make sure that like we're making things better, and prices are not out of whack with reality. But like the interesting thing is just sort of the things that everybody knows about building businesses always. Like you're going to have a point of view on a customer need. You will understand the customer better than the big companies probably. You will you will be nimble in picking these things up and like just very quickly iterating on things that are highly valuable for the customer. So I think the opportunities are huge. So think about the large models as like a technology enabler, like not as the product that you're building.
And what are it's very early days, so we don't really know what this real roadmap will look like. But obviously there's a bunch of times where you say, look, you should actually get the absolute best thing you can, which is the largest possible model that's trained well by a very high elite team, and a huge amount of money has gone into constructing this. What are the cases in which going off and doing your own smaller model might make sense? What are some of the possible lenses or principles on that?
Well, I think, so the tricky thing about the moment right now is like our intuitions are being challenged, and like this is the thing that we face at Microsoft, is we are re-architecting ourselves internally to like more and more use these foundation models, and like have fewer and fewer teams who are like building end-to-end big things themselves. And so like the default intuition is like, oh, I will be able to do better than this big general model if like I have my own data, and like I get to choose my model architecture, and like I train it and fine tune it in like this very bespoke way. And some of the times that's going to be wrong, and some of the times that's going to be right. And so like the thing that I would look at is I'd start with like, can I get access to this big model, and is there a way to do prompt engineering or fine tuning on top of the big model with my data and like for my use case that will like make it performant? And if you can do that, then you probably are architecting yourself in a way where when the foundation model gets bigger and more powerful, you can just sort of swap that in and your application will get bigger and more powerful. You're just sort of inheriting the improvements that are getting amortized across a whole bunch of different applications. But sometimes you're going to have to like build something that's like really custom, like the big foundation models like just don't have the thing in scope that you want to do. Like a good example, for instance, is we are building a whole bunch of models for science right now, where the model architectures and the data for things that are really good for language applications don't help you much in making a molecular dynamics simulation, like where you're trying to get to like fast, quantum accurate models of how atoms interact with one another.
Well, let's linger on science for a bit, because it's actually among the accelerants that I think that probably most of the people in this room have some sense of, but it's super important, which is, science is surprisingly amplified by tooling. And, typically people think of the tooling as, it's a new telescope, or it's a, new collider, or a new da-da-da. But actually part of what we're getting is we're getting the tuning through new tools through software and through these models. So what, we've seen obviously AlphaFold, we've seen Bakerfold, we've seen some of the stuff. What are some of the things that are coming in terms of the science tooling and accelerations?
So there are two categories. Apologies for like getting dorky here. But so there for the computer scientist in the room, there are like two categories of like really hard problems in the sciences. So like you've got this collection of combinatorial optimization problems where you've got something discrete and you want to optimize something about this discrete system, and then you have numerical optimization problems, which are usually systems of like highly nonlinear partial differential equations that describe something about the functioning of like physics or the natural world. And like in both cases, like you have a model of a system that's super complicated, so complicated in fact that all you're able to do is make a bunch of painful compromises about like how you're trying to get to an optimal or near optimal solution to a problem. So with combinatorial optimizations, you typically use a bunch of heuristics. Like you sort of stare at the problem domain for a while and you're like, okay, well, if I do this hacky thing or this other hacky thing, then like I can make this thing that otherwise is NP complete or NP hard like converge faster. Like in these numerical optimization systems, like you just sort of make sort of a whole bunch of different assumptions. It's like I'm gonna like make approximations to like how I solve this the wave equation. Like I'm going to compromise on the resolution of the system. I'm going to compromise on like the number of time steps or like how big the time steps are that I'm making. And so what we are seeing in both of those styles of systems now, and like you can sort of pick up a copy of Nature or Science any given week and see someone using these techniques, is that you can put an AI self-supervised system into these simulation loops where it's learning from the full granularity system. Like you just sort of run it grindingly slow at full resolution, and you train a model that learns something about that domain. And once you have the model, like you put it into the core of the optimization loop, and then things just sort of go faster. There's a bunch of like research papers, like a really good one from folks at Caltech. I think they won Best Award papers, neural differential operators. So they basically came up with a method of solving Navier-Stokes, which is the computational fluid dynamics, partial differential equations. And like they applied it to airfoil design, and they were getting like 100,000x speed ups over the previous best in breed system without losing anything in terms of quality. Extraordinary. And so like I think there's just a lot of opportunity there to and like it means like better medicines. It means like maybe we find carbon fixing catalyst that like we don't know about now. Like I'm just as excited, maybe more excited about that than like some of the things that we get when we finally have a working quantum computer with more than 50 qubits.
Well, yeah, more than 50 logical qubits.
Correct.
Yes, classic thing for folks. What do you think is there's been some reporting on the AI acceleration, AlphaFold, et cetera, on biological things. What do you think are some of the other science areas that people aren't paying as much attention to where you also get that acceleration?
I think it's pretty broad. I would not underestimate, even in biology, how interesting this is for materials design, or things where, in order to transition to a carbon-free economy, it's not just about getting rid of internal combustion engines. You have a whole bunch of materials where either the production of the material consumes a bunch of energy that's carbon intensive, or where the thing itself, like plastics, for instance, require hydrocarbons. And so I think there's a huge number of really interesting materials problems that these AI systems will accelerate.
One of the ones that I heard about relatively recently was actually, in fact, the simulation of certain kinds of fusion reactions relative to using hydrocarbons as the energy chain within them. And the simulation is one of the things that actually increases the probability that we could make that work.
Yeah.
Right.
Correct. Well, and even in things there are a couple of really promising fusion energy companies out there right now, that two that I'm tracking pretty closely, that are making really, really fast progress. And it's one of the things that you would hope would come into existence. If either one of these companies are successful, you should be able to pretty rapidly, small numbers of decades, get a large amount of very cheap energy that's sustainable deployed. And a big part of what they're doing is they need to be able to, in order for them to move fast, to move at software rate, they need to be able to simulate a bunch of stuff at super high fidelity. And so these AI systems there just changes the rate of iteration that they can do, because otherwise you're sort of stuck doing things like ITER, where you have to spend $50 billion building one tokamak, and you'll sort of see if it works or not.
So after this question, I'm going to ask the audience if they have a question or two that they may want to contribute. I have enough for us to be talking through tomorrow. But so I will choose the last one. It's a little bit of you can draw a line, because I know your point of view on this, but you can draw a line from some of the things we've already asked to, you've already answered to this, but I think it's worth calling out. How does the world of knowledge and professional work change? What parts are replaced? What parts are amplified? What parts are modified? And obviously, again, you could answer that for hours. So, given, of course, the book, Rebuilding the American Dream, a bunch of other things, what would be some of the lenses that you would say for what you see coming?
Yeah, and so this is just my opinion. So there are a bunch of different points of view on this. I think the thing, Nero and Aurora and some of the stuff that you're going to see very shortly, notwithstanding, I think one of the things that we maybe have done over the past decade is sort of overestimated the amount of change that AI is going to produce for industrial applications and manufacturing, and sort of these interfaces of technology in the real world. And we've underestimated how much impact it's going to make to cognitive work. And so I think in particular, any repetitive cognitive work, no matter how sophisticated it is, whether it's programming or it's sort of thinking about experiment design, if you're a physicist, or just sort of pick your thing, marking up contracts, diagnosing illness. Most of those things are entirely in scope for these AI systems, and I think people even are going to be shocked this year to see how big a step we're going to make again. Like I think every year, like we get surprised by like what happens. Like like you and I are both friends with Demis, and like even though they're Google and not Microsoft, like you have to just be awed by what DeepMind has done with AlphaFold, like and like the contribution that they've made to science. And so like, we've had Copilot, we have AlphaFold's, protein data bank, last year. Like I think the things coming this year are going to be even bigger, and like most of them will directly impact on cognitive work. And so that doesn't mean that like, they're going to be I don't think they're going to be a bunch of AI like lawyers or AI programmers that are going to do 100% of those jobs. It's that we're going to have real productivity gains for knowledge work in ways that we really haven't had since maybe the onset of the internet.
Yeah, I completely.
And like maybe more than the internet.
Yeah, I completely agree. All right, so question here. Yep.
Thank you, Reid and Kevin. I'm curious, I fully agree when you said that not all applications and innovation is going to come from a bunch of few large companies. You also mentioned about some of the initiatives through API exposure that you think this could be facilitated. What other ideas do you think could help proliferate the ecosystem around? And from your long-spanning career, what are some of the things that you could see from past history as well? That's one. And second, I was curious, for all the initiatives that you've described within your organization, are you looking at any optimization efficiencies at this point? And if there are any thoughts to share on that?
Yeah.
Thank you.
I think both of those are super good questions. I mean, like I will sort of say that this assertion that I have that I don't think big companies will be able to do it all themselves is like part of that's reality and part of it's hope. Like I really do hope for the sake of the world that like you don't have like 2 or 3 ultra rich coastal urban innovation center companies making all of the decisions about like where the like material productivity gains in the world come with and like what problems are important to solve and which problems aren't. Like that just sounds horrific to me. It's my personal bias. So look, I think one of the opportunities for maybe the folks in this room, like entrepreneurs, is even if you probably aren't going to see, just because it's so capital intensive, like a ton of folks building models that cost $1 billion each to train, and we'll be there at some point in the not too distant future, given how things are scaling. I think there's so much stuff like infrastructure that has to get built. So it's not just like, hey, like you build the models, like you wrap them with APIs and like make them accessible to other folks. Like I think it is like an entire machine learning development ecosystem that has to get built around taking dependencies on large models. So helping people with prompt engineering, like fine tuning, like how you manage data privacy and provenance, like versioning, fine tuning data, managing experiments. Like, I mean, like there's sort of a whole set of things that we had to build for sort of the previous generation of machine learning. I think you're going to have like all of those things need to be rethought for foundation models and like that application stack, and you're going to have a whole bunch of new things. Like one of the things we're all probably off building right now that we haven't collectively exposed to the public are safety and moderation layers. So like this thing that sits on top of, or in between the user and Codex and GitHub Copilot, like that's a component that somebody could turn into infrastructure that everybody's going to need. Like we need safety and security and responsibility management for all of these things, especially as the applications and the models get more powerful. So I think it's just a bunch of opportunity. It's interesting, like it's exciting, like it needs to get built. Like even that stuff, like I don't think gets built entirely by Google and Microsoft and Alibaba or whoever else is, or Baidu, who's gonna build this stuff. So, and on your second question, for sure, we're thinking about efficiency. Like, you'd be an idiot not to be thinking about efficiency when you're burning as much like compute as we are. And they're interesting efficiency problems in general. Like, I probably can't say too much specifically about what we're doing. But like, one of the really interesting things, like, there's been a bunch of stuff written about like the carbon footprint of training big models. The interesting thing is that the carbon footprint of training a big model relative to like the rest of the cloud computing footprint of like a big provider is like de minimis. And like the cloud computing carbon footprint, like given how we are able to optimize that energy consumption, like relative to global carbon footprint, also de minimis. But like the exciting thing is like when you can build a foundation model, like opposed to the way that we used to like build things end to end, where you've got 100 different like vertical machine learning stacks inside of a company. Like, if you can take a whole bunch of that stuff and like put it into one component, like that's a really interesting optimization surface area. And so like we think we're actually already getting wins from this, where we can amortize the cost of that training across so many different things. Like, we've got like hundreds and hundreds of features that we're building on top of large models right now inside of the company. And each one of those is like a thing that either wouldn't exist because it would have been too expensive to do before, or impossible, or like something that would have had its own vertical stack, consuming a ton more resources in aggregate than what we're doing right now.
And so the thing I would add to that is, because I think the whole like, carbon footprint of doing these large models is idiotic, is that the application of these models to being energy efficient, like for example, one of the things that DeepMind did, which is study the data centers and figure out how to be more inefficient, is actually net super positive.
100%.
Yeah.
Like, we have these large models right now optimizing like the energy footprint of our data centers.
Yeah. And the results are real.
Yeah, I mean, like we're even doing things like we are selling excess. We're selling excess stored energy in our uninterruptible power supply infrastructure back to the grid, and like using AI systems to bid in the energy spot markets for power.
Yeah, as an example. All right.
Yep.
As you can tell, I can easily and very happily talk to Kevin for hours. Thank you, Kevin.
Thank you for having me.